Welcome back everyone. Today we learn about rate of reaction. Here is an experiment that helps to measure the rate of reaction. And in the experiment we will look at the amount of reactants left over time. A commonly asked question is, what is the purpose of the cotton wool in the conical flask? It is so as to prevent acid from spilling out of the flask, which may otherwise affect data. Does the weighting machine need to be sensitive? The answer is yes, as the machine is capturing the massive gaseous products that are escaping, which is small. Why is the use of beakers not preferred over conical flasks? It is because conical flasks have a narrow mouth that makes acid spraying difficult. The reason why the mass recorded decreases is because products produced are escaping as gases like hydrogen and carbon dioxide. Which reaction shown here is faster? The answer is 2, as the gradient is steeper and it reaches a point where it plateaus faster. The second experiment we will be looking at is measuring the amount of products given off or produced over time. We use a gas syringe for measuring of gas volume, and the conical flask used must be sealed. This shows two different graphs where we have to determine the initial rate of reaction. We determine the initial rate of reaction by looking at the gradient of the graph at t is 0. As time passes, the graph will show a plateau as seen in the graphs, and when that happens, at least one of the reactants has been completely used up. How would we calculate the average reaction rate? We do that by looking at the gradient of the graph, or delta n over delta t. According to the collision theory, the reactants must collide for the reaction to occur, and the collision brings contact between reactants, and it provides energy to break bonds. As seen in the diagram below, particles are constantly colliding, changing direction, and speeding up or slowing down. Let's explain how reaction occurs. An oxygen atom would collide with an ozone molecule. This collision causes an OO bond in the ozone to begin breaking as a new OO bond begins to form. Initially, the energy required for bond breaking is greater than the energy supplied by bond making. And the extra energy necessary for the reaction comes from the kinetic energy of the moving particles as they collide. And as seen in the diagram, bond making supplies energy equal to the energy required for bond breaking. Beyond some point in the reaction, bond making predominates over bond breaking. Bond making supplies more energy than necessary for bond breaking, hence energy is released. All reactions have a minimum activation energy, and if too little energy is supplied, there is no change or reaction. An analogy is as seen below, where if a rolling ball does not have enough energy to get to the top of a hill, it stops and rolls back down. In summary, for a reaction to occur, reactant particles must collide, and the collision brings together the atoms that will form the new bonds. And the kinetic energy of the particles provide energy for the reaction to proceed. The collision must provide at least the minimum energy necessary to produce the activated complex, and it takes energy to initiate the reaction by converting the reactants into the activated complex. If the collision does not provide this energy, products cannot form. When there is a higher collision rate, it leads to greater effective collision rate and increased speed of reaction. Effective collision also means the energy of the particle is higher than the activation energy, and collision brings about chemical reaction. Activation energy is the minimum amount of energy requires for reaction to occur and is labeled as EA in the diagram seen. Let's now look at pressure. When pressure increases, particles are closer together. There is a higher collision rate leading to increased speed of reaction, and pressure can be increased by having a smaller container or have more particles in container. The discussion about pressure only applies for gases, and an example is the formation of ammonia from nitrogen and hydrogen. It is because only gaseous particles can be brought closer together by increasing pressure. When there is an increase in concentration of solution, there will be more particles per unit volume, and due to a higher collision rate, it leads to increased speed of reaction. And it only applies for aqueous solution. When smaller pieces of solid are used as opposed to lumps, there will be more surface area of solid exposed for collision, thus more collisions take place, and there will be an increased rate of reaction. This only applies for solid reactants. At a higher temperature, the particles have higher energy, and they will vibrate and move faster, as well as a higher collision rate, and an increased rate of reaction. Catalysts lower the activation energy significantly such that the reaction rate increases. This diagram shows how the activation energy changes with and without a catalyst. Catalysts are not used up in chemical reactions, and the larger the surface area of the catalyst, the faster the reaction rate. A catalyzed reaction produces the same amount of heat energy as in an uncatalyzed reaction, and the enthalpy will remain unchanged. Transition metals make good catalysts, as seen below in the table with catalysts like iron, vanadium, and manganese. Let's look at some questions. Explain why at 2 moles per dm cube HCl will collect 10 centimeters cube of hydrogen when reacting with zinc, while a 1 mole per dm cube HCl will only collect 5 centimeters cube within the first minute of reaction. It is because due to a higher concentration, there will be a higher rate of reaction. Let's look at another question. Given the scenario below, will the rate of reaction increase when the same experiment is conducted at a higher altitude in the mountain? The answer is no. At a higher altitude, pressure decreases, but the reaction is a solid-acid reaction which does not involve gaseous reactants. Therefore, a change in pressure will not change the reaction rate. An inhibitor slows down a chemical reaction, and an example is tetraethyl lead that is added to petrol to inhibit its pre-ignition. Let's now look at this question. The graph below shows the reaction between 12 grams of magnesium and 50 centimeters cube of 2 moles per dm cube hydrogen chloride. When the concentration of hydrogen chloride decreases from 2 to 1 mole per dm cube, the graph will be as seen below. And in this diagram, when the volume of 2 hydrogen chloride increases from 50 to 100 centimeters cube, it will be as such. Let's look at the second question. We are provided with the scenario as seen below. When the concentration of hydrogen chloride decreases from 4 to 2 moles per dm cube, with magnesium as the limiting agent, the amount of hydrogen produced is the same. The rate of reaction decreases. When the concentration of HCl increases from 4 to 8 moles per dm cube, when the limiting agent is magnesium, the rate of reaction increases. For the first question, when acid is the limiting agent, it affects the rate of reaction, or the initial gradient of graph. It affects the amount of products formed. For question 2, when acid is not the limiting agent, it only affects the rate of reaction. The types of graphs we will be looking at is acids versus carbonate, acids versus metal, and reactive metal versus water. Firstly, try writing chemical equations for the reaction between calcium carbonate and nitric acid. It will be as seen below. Next, write the equation between calcium carbonate and ethanoic acid. The equation will be as seen below. Which reaction occurs faster? The answer is the reaction between carbonate and nitric acid. It is because since nitric acid is a strong acid which has H+ ions completely dissociated, as compared to ethanoic acid, which is a weak acid. The rate of reaction occurs faster when calcium carbonate with nitric acid. With the same concentration, strong acid reacts faster than weak acid. With the same concentration, dibasic acid reacts faster than monobasic acid. The more reactive the metal, the faster the chemical reaction, and in order of metal reactivity, potassium is the most reactive. Which of the following will not affect the rate of reaction between a carbonate and an acid, given the three options below? The answer is atmospheric pressure. Sketch the graph on volume of hydrogen produced versus time for the following acid-metal reactions. The graphs will be as such. In conclusion, the more reactive the metal, the faster the chemical reaction. Sketch the graph on volume of hydrogen produced versus time for the following reactions as seen below. The following are the reactions that the metals have with acids, however do note that copper does not react with dilute acid. For all the reactions, nitric acid is the limiting agent. 0.1 mole of nitric acid produces 0.05 mole of hydrogen. Therefore, these will be the graphs as previously discussed, with the most reactive metal having the steepest initial gradient, and since copper does not react, there will be no hydrogen produced. Write the chemical equations for the reaction between the following metals with water. The equations will be as such. Given the three options below, which reaction occurs faster? In accordance to the metal reactivity, it will be fastest from potassium to calcium. Which of the following will not affect the rate of reaction between a reactive metal and water? The answer will be atmospheric pressure. That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.